I had Nick working on the car, changed out the air filter. And today we'll do chapter 14, some more conjugated alkenes. So total synthesis, oral report lab, you won't be actually, actually let me go with lectures. So there'll be lectures online for today. I made this up, lectures online, just to tell you, don't come to school. And then lab in person, I'm already changing that, lab online. I just got message like 5 minutes ago, no lab today. Lab online. So we're gonna work through this. I have a story to tell the kids. That crazy spring of 2020. Hopefully it's just the spring. So we're all online now. Lab online. And today and tomorrow, we will not have lab. I'm crossing that out. So you'll write up your experiments with whatever data you might have collected already. You may have like your banana oil, proton NMR, but not the 2Ds or something. So you'll use your data first, and then for the data that you haven't been able to collect, I'm going to share that. I'll put it online, and it'll have the proton NMR, and you can label that and then use it as if it was your data, and you'll turn a report into me, just like you normally would, and I'll give you help and instructions along the way. And then the total synthesis experiment, that's a good one. I wish we could do it in person, but I'm going to try to make it as close to like as if you actually did it as possible. So I'm going to be taking like photos and videos, and I'll be doing the experiment, setting it up, and then I'll collect data from the experiment and I'll share that with you, and you'll be doing your report with that data. This way, I want to make sure that you get most of what it would be like to get the lab experience, and I want you to finish this semester with having completed organic chemistry to move on for next year and such. So I'm doing the mechanism quiz this week, kind of like an online exam test run. So I was thinking of ways to do that. I was thinking I'll email the quiz at the start of lecture on Wednesday, so the online lecture. And then I want you to print it out and handwrite out your answers. I'm going to do a color-coded one. and then photo or cam scan it, email it back to me. And I want to see, this is kind of a test run. I want to see how it goes. If you have a tablet, some of you, you can just write your answers on the tablet like you have done in the past with things, and you can then just email it. That's probably easier if you have that option. If you don't have a working printer, it's okay. You could just copy the questions from the computer. Like you'll look at it online when you get the email, and then just write it on blank paper and fill it out. And then if you have your cell phone, you could, I think the Cam Scanner app is pretty nice, or you could just take regular photos of it and email it back to me. And I'll give you like 30 minutes to get it back to me. It's going to be a short quiz. I'm hoping this all works out, and I'll post the quiz questions and key online today. I'm going to get to that, and you're going to be, that'll be the exact same quiz, just like our mechanism quizzes before. So this should be, gaining the skills of this mechanism, and it should, nothing's going to come at you from out of the blue. Oh, and it's worth 5 points, and I'll make it 5 extra credit points. So this is a good test for us, and you get 5 extra credit points if you pull it off. Oh, you know what though? This is weird. I'm putting the answer key online and having you do it. So I'm trusting that you don't just cheat, but I don't know what we're going to do. This is interesting times, right? So try not to cheat, see if you can get it right. And then please let me know of any issues that might cause you, like, oh, my printer doesn't work, my internet or something. We're going to try to figure it out as we go. But you guys are OChemists. You guys are not the complainers. You're going to get it to work. All right, OChem is pretty cool. I know it takes work, but when it starts clicking, it's fun. I think a lot of you have felt that, and I want you to, more of you too, and I want it to happen more. So, and I want you to keep continuing, since we've come such a long way since 12A to start. Let's finish OChem right. So I don't want you to get distracted or get a lower grade than you would have before all this. So make sure you keep up with the lecture videos. That's one of the key things. Think of them as like milk that's about to spoil. If you don't drink it today, it's going to be clumpy tomorrow, and you don't want to drink it then. So don't put off lectures. I know it could be easy with all the distractions now. You can really get caught up in the news and stuff. And then you can be like, oh, I'll look at today's lecture later, or I'll look at this one later. And then If you got like 2 lectures, 3 lectures built up you haven't watched, it's not a good situation. And take notes as you watch the videos. So pause the video. It actually could be a really good learning environment for you. Pause the video, take some notes, work out the problems before I give you the answer key. And then I'm trying this Twitch. I don't even know if it's working right now. We'll see. And if you think there's another better app out there, a better streaming app, let me know. Send me an email. And then, okay, back to chapter 14. So here we go, a little review of the electrocyclic reactions we did last time. So if we add heat to this, you could work out what your product should be and confirm it, work it out for me, see if this is the one you should get, the cis one. And we'd only draw the one product because it's miso. So, and then if I add light, what happens? It gives me the trans products. So there they are. And then here's the other enantiomer of that one. So this one you have 2 enantiomers, a racemic mixture. This one you get the 1 miso. All right, so there's 3 variables in these electrocyclic reactions. Hopefully you've noticed. There's the number of pi bonds. So above this reaction, how many pi bonds are involved? 2 pi bonds. Yeah, 2 alkenes. And it's also a question of number of pi electrons. So how many pi electrons are involved in this one? 4 pi electrons. So that's what you're going to fill in your molecular orbital diagram with. And then the other variable is heat or light. So you can see heat and light will do the opposite to the same molecule. And for heat, you'll use which molecular orbital? The highest occupied molecular orbital, right? Oh, I forgot a period there. And then for light, use what molecular orbital? Boom. The LUMO. Well, it's the LUMO, but the light excites an electron from that LUMO, and now it's in a higher energy. It's not called the LUMO anymore. Now it's a singly occupied molecular orbital, the SOMO. All right, and now the third variable is the cis or trans of the alkenes, or E and Z. So you also need the partial double bond, carbon-carbon bond, to be S-cis. So let's look at that. So here, this alkene happens to be cis. And this one's not cis. Yep, so that's trans. And then this middle bond here is S-cis. It's a sigma bond, but it's got some pi bonding. So we can refer to it as cis, but S for sigma bonding cis. It can rotate, but it has less rotation than other sigma bonds without any pi bonding. If this alkene was, if this was S-trans, this would be over here. You can see how it wouldn't react because they're not on the same side. Okay, and now pause the video and confirm that the stereochem above is correct using our methods, you know, where you draw the p orbitals and all that. So go ahead and check it. Pause the video. Did you pause it? I know you didn't pause it. Pause it and try it, and then come back. Did you pause it? Okay, just kidding. Okay, so along with all the learning how to do an online class overnight, I made the dumbest mistake. On my computer, I have, for some reason, I downloaded the newer version of PowerPoint. So all my PowerPoint files now are read-only, and it won't allow me to create anything new, which is lame, but I've been trying to switch to Google Drive anyways. But so as I was trying to send a help message to the computer guys and girls, I accidentally sent a message about PowerPoint through this software they put on our computer that's supposed to alert like of an emergency, like a shooter on campus. So I had security show up at my office right away, and the dean, I'm like, oh, I'm an idiot. So yeah, here we go. We're gonna start with, I'm gonna start off at the beginning of the chapter 14 outcomes. Last lecture, I skipped to further along into the outcomes with the electrocyclic reactions and the molecular orbital diagrams, because that's pretty cool. But I'm going to go back to the beginning now. So I'm at chapter 14. Chapter outcomes. And the first one is to define allylic carbons. And the second one is their stability. Okay, so here we go. Here's an alkene. This particular that carbon right there, the one that's part of the alkene, is called a vinyl carbon. Great. And then this one, what would you guess it's called? Vinyl as well. The carbon that's just one away from a vinyl carbon, it's called allylic. And we'll see if, because it's right next to the alkene, it can add different reactivity to the molecule. And when you form either an anion, a carbocation, or a radical there, it can have resonance to the pi bond, which affects its reactivity. Before I go into that, I'll say a little bit about vinyl carbons. So, for example, this molecule right here is called vinyl carbon, vinyl chloride, I mean. That's vinyl chloride. It makes sense, the name, right? You got a carbon that's an alkene, it's a vinyl carbon with a chlorine on it. If you polymerize this, you make a long polymer with thousands and thousands and thousands of monomers. Continue on with all those chlorines. Maybe pause the video and draw this out for maybe 10,000 and then come back. Okay, so this one is polyvinyl chloride. So it's many vinyl chlorides, makes sense, right? It's kind of interesting, vinyl suggests an alkene, right? But this has no alkenes, it's just alkanes. But it's because it's made from the alkene, the vinyl chloride. And you've heard of this. This is PVC, polyvinyl chloride. That's what's used for like sprinkler pipes, those white sprinkler pipes you've probably seen at like Home Depot and in your garden. And it's used for a lot of things. So polyvinyl chloride is a very common plastic. And it's also used for pipes, and it's used for records. So you might hear someone say, "Oh yeah, man, you got to get off the digital Apple Music, digital stuff. It takes out all the soul of the music. You got to get your vinyl records and get an old record player and set the needle down." So that the records they're referring to are made out of polyvinyl chloride. That's why you say, "Oh, the record's being released on vinyl and digital." They're referring to this. Okay, so but then back to the allylic carbons. That was the main one for today. The allylic carbons can have extra stability with them because, or when they're either a cation, anion, or radical, they have resonance, so they have extra stability. I'll start with an anion. So let's say we have, I'll do this. So we have two hydrogens here. And I added like N-butyl lithium. The N-butyl lithium can deprotonate this allylic carbon the anion there, butane bastard gas. And this reaction is actually product favored. The reason why is the pKa of this allylic carbon is more acidic than you might guess. Its pKa is about 40. And what's the pKa of the butane gas? About 50. So our K equilibrium for this, 10 to the 50 minus 40. 10 to the 10, very product favored. Okay, so why is it more acidic? One way you can think of it is if you think of it before it reacts, you could say, oh, this sp2 carbon is more electronegative than a regular sp3 carbon like this one here. So the sp2 carbon could be withdrawing electron density a little bit towards it, making this bond a little weaker, a little more acidic. Another way you can look at it is looking at the product side, the conjugate base. Can it be stabilized in any way? Yes, it can, because it's got a lone pair, single bond, double bond. So it's in conjugation with pi bond, boom, right like that. So the anion, it's got some stability to it, makes the acid a little stronger. So you can see how the allylic position right next to the alkene, it can affect its reactivity. So that's an anion, and so what else did I say I would show you besides anions, allylic anions? What else? Which one do you want? Okay, Ryan, you wanted donuts? No, I mean the anion. There's no allylic donuts. We'll do carbocations for you. All right, here we go. We got the carbocation. Let's say you have a carbocation that is here. This carbocation is at what? Methyl, primary, secondary, tertiary? It's a secondary carbocation. So you can get resonance for this. It's going to look a little different than the anion resonance where you have extra electrons pushing the pi bond. On this one, you're going to have, think of it as a hinge and the pi bond swinging over. And when you look at this, you might think, oh no, this isn't good. This is a primary carbocation. We can't have primary carbocations or 2-ion energy. But it's not just this. It's, resonance isn't two molecules in equilibrium. Resonance describes a single molecule. So really, an understanding of this, you should think of it with like a resonance hybrid, like this, where you have like a delta plus here and a delta plus there. Okay, and so you can think of it as like a secondary and a primary, or like a primary and a secondary carbocation. So you might, I don't know, I would estimate that might be like a regular, just tertiary carbocation because it's got both secondary and primary carbon sharing the positive charge. So yeah, that's going to be some extra stability to that one. Okay, let's go on to the next one. Which one should we do next, Ryan? Ryan, which one would you like? We did anions, resonance stabilized, allylic anions, resonance stabilized, allylic carbocation. Now what would you like? Peanut butter. No, that's not the, yeah, so, yeah, Sarah, what would you like? Sushi? No. Ken? Do you want to? I know the Minecraft Labs thing sounds cool, but let's get back. Okay, we're going to do radicals. Oh, it's so hard to tell a joke to an empty classroom. All right, here we go. We can have a little radical. And we haven't seen this yet, but radicals can have resonance. Kind of cool. Remember when I first learned this, I thought, I don't know, when I first learned radical mechanisms, I thought they were pretty cool, the half arrows. I liked it. And now with this one, with the resonance, I was excited by this too, hopefully you like it. So I've got 2 electrons in this pi bond here. One of them is gonna meet me halfway with that one, right? To make the pi bond there. And then just show the pi bond character there. The other one goes there. There we go. Pretty cool, huh? So this radical is sort of like a tertiary carbon radical because it's part secondary carbon radical plus primary carbon radical. So let's try a more complicated one. What do you want to do? You want to do a complicated carbon radical, carbocation, or a anion? one's going to have a lot of resonance. There we go, that's a good one. So try to draw all the resonance for this particular carbocation. So when I say that, I mean like pause the video if you're watching it not live, and then come back to it. See the answer? Okay, and we're back. So I'm going to imagine a hinge here and the pi bond swinging out. There we go. So I have an allylic carbocation here. And now I've got another allylic carbocation, huh? So it can also resonate again. And once again, it's allylic. So it has one more resonance structure. Which can be seen by having a hinge here, swinging over this way. And that's all. So this carbocation is, the positive charge is shared over 1, 2, 3, 4 different atoms. So it's real stable, more stable than tertiary carbocation. And what I'd like you to do now is pause the video and do-yo on your own the radical and the anion of this guy. Next up, right here, is outcome 4. And outcome 4 talks about, it's a new reaction in which we're going to try to add a bromine to the allylic carbon. If we start with an alkene like this, and we just add bromine, say carbon tetrachloride, will we get allylic bromination? Will it put a bromine here, or will something else happen? Yeah, something else happens. You're going to get the anti-addition across the pi bond. And the reason for that is the concentration of bromine is too high for allylic bromination. It's just too high of a concentration. It'll just run into the pi bond and react there. But if we can get this concentration of bromine really low and we shine light at it, then before a bromine molecule can run into the pi bond, the light might make it into radicals. And then when it's in a radical form, that's when I'll get allylic bromination. So let me show you how you do that. So there's a molecule we're going to use to accomplish the low concentration of bromine. It's called N-bromosuccinimide, and we use NBS to refer to it. So what is NBS? NBS is N-bromosuccinimide. And it creates a low concentration of bromine, or makes a low concentration of bromine. So what does it look like? Here's the molecule. If I just put a hydrogen on the nitrogen, that's succinimide. If I put a bromine there, now it's N-bromosuccinimide. When you have N-bromosuccinimide, or just NBS, when you have NBS, there's going to be a little bit of HBr around. It's in for some reason there's a little bit of acid impurity in it. And because of that, the NBS winds up forming N-bromosuccinimide and Br2. But the reaction is very slow. So you wind up with a very low concentration of Br2. This is a slow reaction. And the reason why it's slow is we pick a particular solvent to keep it not very soluble. Okay, so we'll use a solvent. You're going to see that this solid isn't very soluble in it, but a little bit will dissolve, and when a little bit dissolves, it can react to make a very low concentration of bromine. And then the equilibrium stops there, but then if that bromine reacts, then a little bit more dissolves, so it's kind of a slow process. It's set up well for that. Okay, and then this mechanism, you don't have to know this mechanism, but it's online. It's actually not that bad of a mechanism. So, not responsible for this mech, but it's on our mechanism database. Okay. After this point, though, I want you to do the mechanism. Before I do the mechanism for this one, I'm going to do a quick review on something. Why is it that when I add bromine and light, I get mostly secondary bromine and a lot less primary? So why was it? Remember we talked about this, we spent a lot of time on this one, introduced the Hammond postulate. So because of the mechanism, we said, okay, first, the bromine breaks apart into radicals. Initiation. Then the bromine could react with a primary hydrogen. Can you meet me halfway? And HBr, and this one is endothermic. Okay, and it's a propagation. We started with a radical, we ended with a radical. Another option is to take a hydrogen off the secondary carbon we got another secondary carbon radical, and this two is endothermic. And that's the key reason why we get more secondary carbon radical than primary. Doesn't seem like it maybe yet, but remember when you look at the reaction coordinate diagram, you can make your secondary radical and your primary radical and HBr. The activation energy for the secondary carbon radical is much lower because this transition state looks like the products mostly. So this looks like a secondary carbon radical mostly, whereas that one is higher energy because it looks like a primary carbon radical. And is this reaction then, it's producing the secondary radical more, which then produces the final secondary bromide more. Is this reaction, do you think, under kinetic control or thermodynamic control? We're saying the major product comes from the one with the lower activation energy, the faster to form radical. So this is kinetic control. And so it has to do with the radical energy. So going back to the MBS stuff. So if we add the NBS, carbon tetrachloride, it's not very soluble in carbon tetrachloride, you know that? And one other thing too, light. Okay, so the NBS is not very soluble in the carbon tetrachloride. When a little bit of it dissolves, it can form a low concentration of bromine. And when that low concentration of bromine is formed, there's not a lot of it, enough of it to run into the pi bond. So before it runs into the pi bond and does the anti-addition, it can get hit with a photon of light and made into a radical, and now it's on a different pathway, it's on a radical mechanism. So let's see the mechanism for that. So we have the NBS, it's creating the low concentration of bromine. And then at that point, we'll start a normal radical halogenation type of mechanism. So the bromine starts off as just Br2, and then the light hits it and it can become radicals. Okay. So what kind of step is that? Initiation, propagation, termination? That's an initiation. Started with no radicals, ended with radicals. All right, and now for our alkene, the bromine's gonna remove a hydrogen, and it's gonna do it from a hydrogen that will result in a lower energy radical. It'll do that most. So the lower energy radical then will be lower in energy, so it's activation energy leading to it, which it looks like is lower in energy, lower activation energy, faster reaction. So here we go. Okay, so it shows the allylic hydrogen, not one of the vinyl ones. The reason why it chose that one was because when it makes the allylic radical, it can be stabilized with resonance. So this is much lower energy than if we just took a hydrogen vinyl position, it wouldn't have resonance. If you're not sure that it wouldn't have resonance, try to draw the vinyl radical and see if you can draw resonance for it. And this again, yeah, this one's a propagation step because we started with a radical, we ended with a radical, and this radical is stabilized by resonance. Okay, and then I bet you can guess the rest of it. It can now react with the low concentration of bromine that's around. And another propagation. And the terminations can occur. You're good at drawing terminations. After the concentration of this guy gets low because it's running out, or the original alkene, it's made into product. Its concentration's dropping, then you'll get some terminations ended off. Okay, that's a little bit of bromination, kind of cool, huh? Key thing is just the concentration of bromine. You have to come up with a creative way to keep the bromine concentration low enough so that it'll be more likely hit by a photon of light and radicalized than it will run into the alkene just due to anti-addition. Let's try a more complicated example. What time do we get to? Okay. Okay, so this one's got a little more going, right? It's got a extra carbon here. But once again, what's going to happen is the NBS is going to make a low concentration of bromine, then that low concentration will get hit with a photon of light, and it will then it'll try to make the lowest energy radical. So what would be the lowest energy radical for this guy? This secondary allylic. So I'm going to just show you how I can get my products without doing the entire mechanism. But practice this mechanism. That might be a good one to have on the exam because it's reviewing the radical stuff again. So if I can imagine I get to this radical, and that radical has resonance. And I can think of it this way, and I can also think of it this way. There we go, right? And then those could react with bromine to make our products. So what kind of products am I expecting? I'm expecting this one that can form from the radical that was initially formed right there, right? And then I expect the wiggle there because the bromine can come from either side, get that stereo, get the racemic mixture of those two enantiomers. Then on the other ones, we could see how the bromine can attach to this end. And you can get this one plus this, the cis and trans. These two you can call, if you wanted to abbreviate it, or not approximate equal to, you can wiggle that to say, oh yeah, that's the cis and trans alkenes.
So you can get a lot more products when you have a little bit more complicated molecules. So with these ones, I usually keep it pretty simple. I usually make them pretty small. Like on the exam, I'll probably maybe just have you do the 3 carbon ones where you just get the one product. And you don't have like a situation where like one of them's major. They're all about major. So since you don't get like one dominant one, it's not always the best reaction for you if you wanted to do something like this. It's because it's reactions under kinetic control, so it's more about the fastest reaction produces the major product, but the rate for both is about the same. Okay, so allylic brominations were done. Let's move on to the next outcome is just kind of something you should know. Outcome 5. The allylic position, if you have a leading group on an allylic position, it makes the electrophile much stronger. So here is the allylic carbon. There's the leading group. This, in terms of electrophiles, it's a much stronger electrophile than just a regular alkane electrophile. They're both primary electrophiles, but this one is a primary allylic electrophile. This is just a primary electrophile. And yeah, having an allylic group there makes it much more reactive. So like this you can use in the bench in the lab, but sometimes these allylic ones are so strong of electrophiles you want to use them in the fume hood. And why would that be? So electrophiles are electron loving. They're attracted to nucleophiles, the negative charge things usually. So if you're electron loving, that means what charge do you have? You have a positive charge. So there's a positive charge here, and it's more positive for this one than for that one. And why might that be? You can think of it in terms of this is an sp2 carbon, and this is an sp3 carbon, and the sp2 carbon is more electronegative than the sp3. Thus, that's more reactive. This is a primary allylic. It can actually do SN1. Normally we say, oh, primary carbons can't, electrophiles cannot do SN1 or E1 because they can't make the primary carbocation. It's too high energy. Why would this maybe be able to make a carbocation? Well, that's because the carbocation have resonance. Hopefully this looks weird to you, and you think, no, that's wrong, we can't have that. Primary carbocation, no. But now that we've learned about allylic positions, we can see, oh wait, it's not just an isolated primary carbocation. It's a combination of the two. So it's got plus 1/2 on this carbon, plus 1/2 on that carbon. So I think of it as like a secondary carbocation. Thinking when I know when you're watching live, but when I edit this video down after lecture, I'll be able to like take out or speed up the whiteboard stuff. So I'll probably be able to take my hour and 20 minutes and have it be more condensed. I could just like shove more info in your head, but now that you have so much more free time, I figure I'll just teach you guys like 3 times as much as I normally do and expect that on the exam. We're gonna be normal. But here we go. Let's go to, outcome 6. So on outcome 6, we talk about conjugated pi bonds, pi bonding is lower in energy than non-conjugated. It kind of goes along with what you've been seeing. You've been seeing a lot of cases where you have like a base, and if it has resonance to stabilize, it spreads out its negative charge, it stabilizes it, right? So when you have pi bonds in conjugation, they can resonate, and they're lower in energy than when they can't. So let's look at an example. If I compare, for example, this alkene, diene, to this one, they're both both 6 carbon molecules with 2 alkenes. One of them's lower in energy. Which one? This one. So why is that? Well, here is a pi bond, or I'll say double bond. Double bond, single bond, double bond. So when you have a double bond, single bond, double bond, that's conjugation. So these can resonate. You can see the resonance forms are crazy. They're like real minor resonance forms, but they do affect it. Like we said before, there's partial pi bonding there. So there's conjugation. These 2 alkenes are conjugated. That results in them being lower in energy than these are non-conjugated. So why is that? Why are they non-conjugated? I've got a double bond here, then a single bond, oh, another single bond. I needed a double bond right there. So I can't draw resonance for this. They're not conjugation. So that one's higher in energy. How would I experimentally know this? I can't just like say it's because of resonance. You gotta have an experiment behind it. I can know it by doing this. What happens if I add excess hydrogen gas, palladium on carbon, say methanol, to both of them? What will I produce? In both cases, I'll just produce the N-hexane, 2,4,6, 2,4,6. And these are both exothermic. They'll release heat. And if I compare these heat, I'll call this heat 1 and heat 2, they're not going to be the same. So you can do this reaction like measuring the heat produced with a calorimeter. And which one's greater? And which one, do you think heat 1 is a larger amount of heat or heat 2? Well, let's think about it. They both end up at the same energy. They're both the same molecule. And I said the conjugated one was lower in energy and the non-conjugated one was higher in energy. So this is heat 1, whereas this is heat 2. So which one's greater? Heat 2. So experimentally you can figure out, oh yeah, they both became the same thing. They stopped at the same energy level. But this one released more heat, so it must have started higher in energy. You got it? And this energy difference between conjugated and non-conjugated, we're going to see a lot of that this chapter. And then the next couple chapters, we're going to look at it in a cyclic case where it's going to have some differences to it because of the cyclic nature. But we'll be looking at the energy stabilization of conjugation a lot. All right, so cis and trans. Outcome 7 is talking about S cis and S trans bonds. We've already talked about that. I think you got the idea of it. And then, oh, the next one's a really good one. 1,3-butadiene. All right, so I've got 1,3-butadiene. 1, 2, 3, 4. See the nomenclature there? I won't have you name dienes or trienes. I'll just have public. Did I already have an alkene on the exam? Probably an alkyne next exam anyway. So, all right. So we got 1,3-butadiene. For this reaction, I bet you can come up with the possible products just by your knowledge of mechanisms. So try to work out the mechanism. I'll go like this, HBr there. Let me give you a couple tips and then I want you to try to do it. So are we under acidic or basic conditions? Acidic conditions. HBr is a very strong acid. So what's going to happen first? Probably protonate something, right? And what kind of charged organic intermediates do we expect? Positive charge. Okay, so pause the video and try to work out what might happen here. Do the first step of the mechanism, look at it, consider things, see if you can figure out what the final products will be. I guess on the Twitch versus live people, I'm just going to do it. So I have a couple options here. I can imagine a hinge here and the pi bond swinging out, and that would be wrong. I'll just draw it out wrong first. So imagine if I have the hinge there, if I swing out this way, I would make a primary carbocation and the bromide. And we know primary carbocations are very high energy. But we did learn today that, oh, if they have resonance, they can form. Does this one have resonance? Can this? No, no resonance. Primary carbocation, too high in energy to form. So that is wrong. Make sure you know that it's wrong. Don't think because I wrote it, it's right. It's wrong. Okay, if you can't read it because I was quick and sloppy, it's okay because you shouldn't. It's bad for you. All right, the next one though. What about if I have the hinge here on the end and I swing out the pi bond? This is just like Markovnikov stuff, right? If I swing it out there, then I will get this carbocation. And does that carbocation seem reasonable? Like you can make it? Yes. This one is a secondary allylic carbocation. So that one's relatively low in energy. We can form that. And you might have already thought, oh yeah, I can see what happens now. The bromide just adds the secondary carbocation, just like a regular Markovnikov addition to an alkene. But there's a little more on this one. This guy has resonance since it's allylic. As you can see, hinge here, this can swing that way, right? So we're going to get more than just the secondary bromide. We're going to get some primary bromide too. So here we go. We can get that. And we're gonna get that one and the other one too. This other one can come from the, this doesn't have to always be in that conformation, it can be like that, right? And then it has resonance. Like that. Okay, so we're gonna see, we get 3 products from this, and we can actually determine what the major product is by adjusting the temperature of the reaction. And but I'm gonna pause for now today there. Let me see, what time is it? Yeah, I went over a little bit, but we're in virtual time now. No, just kidding. So I'm gonna pause there, and the next lecture, I'm gonna talk to you about why this could be, you could adjust which is the major product of these 3 by changing the temperature of the reaction. It's pretty cool stuff, you'll see. So I'll see you then.